A surprising study found hints of biological activity on a distant planet. Now, scientists say there's more to the story. A tiny sign revealed in April seemed like it might change the universe as we know it. Astronomers had detected just a hint, a glimmer of two molecules swirling in the atmosphere of a distant planet called K218b, molecules that on Earth are produced only by living things. It was a tantalizing prospect, the most promising evidence yet of an extraterrestrial biosignature or traces of life linked to biological activity. But only weeks later, new findings suggest the search must continue. It was exciting, but it immediately raised several red flags because that claim of a potential biosignature would be historic, but also the significance or the strength of the statistical evidence seemed to be too high for the data, said Dr. Luis Wellbanks, a postdoctoral research scholar at Arizona State University's School of Earth and Space Exploration. While the molecules identified on K218b by the April study, dimethyl sulfide, or DMS, and dimethyl disulfide, or DMDS, are associated largely with microbial organisms on our planet, scientists point out that the compounds can also form without the presence of life. Now, 3 teams of astronomers not involved with the research, including Wellbanks, have assessed the models and data used in the original biosignature discovery and got very different results, which they have submitted for peer review. Meanwhile, the lead author of the April study, Niku Madhusudan, and his colleagues have conducted additional research that they say reinforces their previous finding about the planet. And it's likely that additional observations and research from multiple groups of scientists are on the horizon. The succession of research papers revolving around K218b offers a glimpse of the scientific process unfolding in real time. It's a window into the complexities and nuances of how researchers search for evidence of life beyond Earth, and shows why the burden of proof is so high and difficult to reach. Noisy data located 124 light-years from Earth, K218b is generally considered a worthy target to scour for signs of life. It is thought to be a Hycean world, a planet entirely covered in liquid water with a hydrogen-rich atmosphere, according to previous research led by Madhusudan, a professor of astrophysics and exoplanetary science at the University of Cambridge's Institute of Astronomy. And as such, K218b has rapidly attracted attention as a potentially habitable place beyond our solar system. Convinced of K218b's promise, Madhusudan and his Cambridge colleagues used observations of the planet by the largest space telescope in operation, the James Webb Space Telescope, to study the planet further. But to scientists at the University of Chicago, Dr. Raphael Luke, a postdoctoral scholar in the university's Department of Astronomy and Astrophysics, and Michael Zhang, a 51 Pegasi B, Burbage postdoctoral fellow, spotted some problems with what they found. After reviewing Madhusudan and his team's April paper, which followed up on their 2023 research, Luke and Zhang noticed that the Webb data looked noisy, Luke said. Noise caused by imperfections in the telescope and the rate at which different particles of light reach the telescope is just one challenge astronomers face when they study distant exoplanets. Noise can distort observations and introduce uncertainties into the data, Zhang said. Trying to detect specific gases in distant exoplanet atmospheres introduces even more uncertainty. The most noticeable features from a gas like dimethyl sulfide stem from a bond of hydrogen and carbon molecules, a connection that can stretch and bend and absorb light at different wavelengths, making it hard to definitively detect one kind of molecule, Zhang said. The problem is basically every organic molecule has a carbon-hydrogen bond, Zhang said. There's hundreds of millions of those molecules, and so these features are not unique. If you have perfect data, you can probably distinguish between different molecules. But if you don't have perfect data, a lot of molecules, especially organic molecules, look very similar, especially in the near-infrared. Delving further into the paper, Luke and Zhang also noticed that the perceived temperature of the planet appeared to increase sharply from a range of about 250 Kelvin to 300 Kelvin, 9.67F to 80.33F or minus 23.15C to 26.85C. In research Madhusudan published in 2023 to 420 to Kelvin to 199.93F or 148.85C in the April study. Such harsh temperatures could change the way astronomers think about the planet's potential habitability. Zhang said, especially because cooler temperatures persist in the top of the atmosphere, the area that Webb can detect, and the surface or ocean below would likely have even higher temperatures. This is just an inference only from the atmosphere, but it would certainly affect how we think about the planet in general, Luke said. Part of the issue, he said, is that the April analysis didn't include data collected from all 3 Webb instruments Madhusudan's team used over the past few years. So Luke, Zhang, and their colleagues conducted a study combining all the available data to see whether they could achieve the same results, or even find a higher amount of dimethyl sulfide. They found insufficient evidence of both molecules in the planet's atmosphere. Instead, Luke and Zhang's team spotted other molecules, like ethane, that could fit the same profile, but ethane does not signify life. Disappearing evidence, Arizona State's Wellbanks and his colleagues, including Dr. Matt Nixon, a postdoctoral researcher in the Department of Astronomy at the University of Maryland College Park, also found what they consider a fundamental problem with the April paper on K218b. The concern, Wellbanks said, was with how Madhusudan and his team created models to show which molecules might be in the planet's atmosphere. Each molecule is tested one at a time against the same minimal baseline, meaning every single model has an artificial advantage. It is the only explanation permitted, Wellbanks said. When Wellbanks and his team conducted their own analysis, they expanded the model from Madhusudan's study. Madhusudan and his colleagues didn't allow for any other chemical species that could potentially be producing these small signals or observations, Nixon said. So the main thing we wanted to do was assess whether other chemical species could provide an adequate fit to the data. When the model was expanded, the evidence for dimethyl sulfide or dimethyl disulfide just disappears, Wellbanks said. Burden of proof. Madhusudan believes the studies that have come out after his April paper are very encouraging and enabling a healthy discussion on the interpretation of our data on K218b. He reviewed Luke and Zhang's work and agreed that their findings don't show a strong detection for DMS or DMDS when Madhusudan's team published the paper in April. He said the observations reached the 3 sigma level of significance, or a 0.3% probability that the detections occurred by chance. For a scientific discovery that is highly unlikely to have occurred by chance, the observations must meet a 5 sigma threshold or below a 0.006% probability that the observations occurred by chance. Meeting such a threshold will require many steps, Wellbanks said, including repeated detections of the same molecule using multiple telescopes and ruling out potential non-biological sources. While such evidence could be found in our lifetime, it is less likely to be a eureka moment and more a slow build requiring a consensus among astronomers, physicists, biologists, and chemists. We have never reached that level of evidence in any of our studies, Madhusudan wrote in an email. We have only found evidence at or below 3 sigma in our 2 previous studies, Madhusudan et al., 2023 and 2025. We refer to this as moderate evidence or hints but not a strong detection. I agree with Luke and Zhang's claim, which is consistent with our study, and we have discussed the need for stronger evidence extensively in our study and communications. In response to the research conducted by Wellbank's team, Madhusudan and his Cambridge colleagues have authored another manuscript expanding the search on K218b to include 650 types of molecules. They have submitted the new analysis for peer review. This is the largest search for chemical signatures in an exoplanet to date, using all the available data for K218b and searching through 650 molecules, Madhusudan said. We find that DMS continues to be a promising candidate molecule in this planet, though more observations are required for a firm detection, as we have noted in our previous studies, Wellbanks and Nixon were pleased that Madhusudan and his colleagues addressed the concerns raised, but feel that the new paper effectively walks back central claims made in the original April study, Wellbanks said. The new paper tacitly concedes that the DMS detection was not robust, yet still relies on the same flawed statistical framework and a selective reading of its own results, Wellbanks said in an email. While the tone is more cautious sometimes, the methodology continues to obscure the true level of uncertainty. The statistical significance claimed in earlier work was the product of arbitrary modeling decisions that are not acknowledged. Luke said the Cambridge team's new paper is a step in the right direction because it explores other possible chemical biosignatures. But I think it fell short in the scope, Luke said. I think it restricted itself too much into being a rebuttal to the Wellbanks paper. Separately, however, the astronomers studying K218b agree that pushing forward on researching the exoplanet contributes to the scientific process. I think it's just a good, healthy scientific discourse to talk about what is going on with this planet, Wellbanks said. Regardless of what any single author group says right now, we don't have a silver bullet. But that is exactly why this is exciting, because we know that we're the closest we have ever been to finding a biosignature, and I think we may get it within our lifetime, but right now we're not there. That is not a failure. We're testing bold ideas.